It's a great pleasure, great honor to be here in Japan to be speaking to you guys. ご紹介いただきました。
Thank you very much for your kind introduction. My name is Keita Kanno from QunaSys. I am CTO. Today, I think this is the second time to support this event by QunaSys. So I'd like to talk about what we have done so far for the last 12 months, especially the ChatGPT expansion and also the new products application. So novel products and community building. So these are some things which I'd like to take you through. So QunaSys was established in 2018, and this is a 5th year anniversary. And in Japan, it was established. But we do have the business, or we are expanding the business in Europe. We have the advisors from the University of Osaka, and together with the 50 colleagues, we are especially involved in the quantum chemical calculation. That's what we do for our R&D. And this is our mission. So we try to maximize the power of quantum computing to have the commercial application. In particular, what we have been focusing on is chemistry, so application in chemistry. The industrial application, I think the most promising application is chemistry. So quantum computing is actually able to express the superpositions of the electrical states. But basically, this is in the computer and also the molecular electronic state, and there is a kind of a good relation. So using that relationship, maybe Q or E, or maybe the phase estimation algorithm, especially this quantum phase estimation algorithm against the complex molecule, this is quite efficient and also accurate energy calculation to be done. And also our mission is trying to apply to the industry. So we always try to explore the new possible application. And at the very end, I'd like to talk about this new application, which is a natural frequency application. And yes, just like the natural frequency analysis, we are also trying to explore some new upcoming the application. So let me talk about the chemistry. To really enable the quantum computing, I think maybe to really to really be ready to use quantum computing, there are different stages. Well, at the beginning, so what is quantum computing? What can be enabled by quantum computing? That's a learning stage. And then you are trying to identify the use cases within yourselves. What kind of use cases do you have? And also if we try out, what is going to happen? And then at the very end, you are developing your own algorithm sometimes. So for that steps, we can offer different proposals. So let me take you through these stages so that you understand what we can offer. The first one is at the learning stage. So we have built the community called Q Park. Over 50 members are inside of this Q Park for the last 3 to 4 years. And within Q Park, the lecture learning materials can be offered, or maybe you can participate in the networking and collaboration opportunities so that you learn the cutting-edge quantum computing. And also using simulator, you can do the hands-on, or maybe you can actually use the real machines of the quantum computing. And then also within the community, you can jointly collaborate for your research. Also, in this year, as a new initiative, all the participants of the Q-Parts are heard and trying to really have the use case classical and use case quantum. For classical, so maybe the classical computing can enable, and also the quantum computing, only quantum computing can do, or maybe quantum computing cannot do. So these are the projects which we are trying to identify. And also quantum computing, you cannot go to algorithm development from day one. So what kind of what kind of activities do we need to have for the algorithm development is something which we can explore. Another program is called, yes, the quantum computing can be used to solve the social agenda. So how and to what extent can we get the answers? How much we can solve those social issues? So quantitatively, we are trying to measure how much this can do, and this is called SDQs. And currently, we are soliciting the members. If you participate on this initiative, you can pick the topic, and also maybe the report can be shared. So I hope if you are interested, you can participate on either QPark or maybe SDQs. Also, QPark is a community. So, of course, sometimes we cannot meet all the companies' needs because it's just a community. So that's why we have individual QPark called iQPark. Under this scheme, for each individual corporation, we have one-on-one use case to exploration and also trying to develop the roadmap together with QunaSys. So this is some of the contents, and yes, those contents can meet the demands. So I hope that you can consider this as one of the options. So that is the QPark. Next is how you can leverage those learning. So let me talk about the products. So in 2021, we have released the public beta called Kamui. And Kamui is using the quantum computing algorithm for chemistry software. So using JSON or Python SDK to really get the algorithm or molecular information to be entered. And Kamui is going to convert them into the quantum circuits. And then you are going to run that in the quantum computer. Kamui is already used by many companies, and there is already a thesis like Mitsubishi Chemical or maybe the Toyota Central Lab. And also within QPark, there are some use case exploration and many applications already presented by the member companies using Kamui. So Kamui, as users, well, yes, since this is a cloud, so it's a certain level of the black box, but some users would like to know a little bit more. Or maybe it should be simpler. It doesn't have to be installed, but just simply want to use Kamui. So this is a little bit contradictory, but we have a lot of customer voices, user voices. So for the core user, we offer Curie parts. This is an open source Python library. So this is for the core users. On the other hand, yesterday we have released Curie. And this is using Kamui functions through GUI. So you can use GUI to use Kamui functions. Let me go one by one. First one is a Curie parts. So development of the quantum algorithm developer is our target users. So there are different functions or features of the quantum algorithm you can pick. You can actually combine or you can add your own coding to use it for the simulator or maybe for the actual quantum computers. So it's a high layer library, but it can maintain a good performance. This is open source, so I hope you can use it. The other one is Curie. And on the right-hand side, this is actually screenshots. And yes, coming to this URL, you can actually access to this. Curie, as I mentioned, this is on the web browser. You don't have to write code, you don't have to install, but you can experience the quantum computing. VQE is a baseline. So VQE is the algorithm. So it's not just for the grounded state, but you can also calculate excited state as well to really learn the quantum algorithm. I hope you can access to this site. We cannot do the simulation without licenses, but you can try out to see how it works. So that's being the community and also products. So lastly, I'd like to talk about the research of the algorithm. So far, since the establishment, we have already a lot of joint research partners and many research theses. 39 papers have been already published. Many baseline is based upon the VQE algorithm. Some of you have heard about this, but the noisy quantum computing trying to simulate the ground states. So that's the algorithm to be used for. And yes, we use classical and quantum computing. Quantum computing is measuring the energy, and also the classical computer is used to really see where the energy level is low. So trying to really explore the lower energy level, and that should be set as a ground state. Since it's less noisy, and this is noise resilient. Well, VQE algorithm have been applied for different applications, and we have developed the algorithm. For instance, the molecular dynamics, so the force to be applied to the molecule is also simulated. And also, this is now applied to the electromagnetic field. And we actually developed the algorithm. In the photochemistry, well, we have to really simulate the electric situation. And also for the solid materials, the band structure is essential. And based upon VQE, we can develop the method to calculate band structure. However, VQE itself also is having issues. There are two issues at the algorithm level. One is energy evaluation. There are too much sampling errors, so the number of the samples or number of the shots have to be many, because otherwise we cannot get a right answer. And the other one is even though we evaluate the measurements of the energy, it's too many steps, so that's why we need to really optimize the process, because otherwise it is quite a lengthy simulation time. This is totally irrelevant to the noise of the device. So even though there's no noise on the device, we need to solve these issues. So against these issues, we are trying to modify or improve VQE, or maybe replace VQE. We have two approaches. First one is an improvement of VQE. So sampling errors to reduce, we have the grouping. So as a new method, we developed this idea is a QPAC challenge. Our hackathon is come from this. So the blue and red is existing method, and also the this is a 40-bit qubit, but after that the ground process is too much, so it's not really working. So 40 qubit, that was also the number in Fujitsu simulator, but we have to go above, because otherwise we cannot take the quantum algorithm advantage. So because if it's too heavy, we cannot really use it. So even though it can go to 60 qubits, we can still work. So it is quite comparable to the other methodology. On the right hand side, this is double quantum bit used, and all the operators can be measured at the same time. And if we do this, maybe it can be 10 times faster VQE. So it's already made in paper. Also, the replacement of the VQE. This was also introduced last year as well, about QSCI. We actually made the paper, published the paper, and VQE is a classical and a quantum hybrid. So we have to work more with the classical so that it can be more accurate and more reliable. Yes, this is a 8 qubit is used for our experiment, and usually it has a huge error, but it's one hardly, but it's double digits reduction. So CISD, compare against CISD, for multiple runs, I think it's better than the classical. Also, as a replacement of VQE, it's more specific to the applications. So yes, the time development can be tracked, or green functions, we can actually measure or compute the green function. And also the right-hand side is vibrational property of the molecular can be computed. So we don't have to be dependent on the VQE. Together with Fujitsu and others, we are now making a proposal to replace VQE. So I think I have talked about RFQC. Well, the partial error correction, how we are going to use this is a huge challenge. And bit flip code, which is a simple error correction method, and also maybe error correctable methodology can be considered. And also the right-hand side is a new error detection scheme, and maybe this is better than the conventional way to detect the errors. Also, I think once we are able to the fully error correctable, I think this FTQC already you actually enter the molecule, and then let's say if it's a 100, then you can actually get the ground energy level with just one day. So if you can explore the use cases, how much time, how much quantum bit you need, I think now you can actually get those. And also this FTQC itself is also going to be improved. So I have been talking about the chemistry, but this is totally irrelevant to this. So this is a new way to use the quantum computing, and this is the application to the natural frequency. So natural frequency, as you may know, is like a building or a bridge or maybe the cars or airplanes designs. So we are going to enter the vibration, which is quite similar to the natural frequency. Maybe it can break or it can produce noise. So using that algorithm, we can use the algorithm for this type of computation. So yes, it's quite a simple mock-up or model. This is 10 to the power of 38, or maybe 10 to the power of 50. For a few hours, you can actually calculate the natural frequency. So that's something which we are working on. And this is a one-dimensional. So that's why it is not industrial application. But from here, we are trying to really advance this so that it can be used for more complicated application. And then we try to figure out how long this is going to take. So this near term, the FTQC, and this is not just used for the chemistry, but maybe you can actually use for the different applications, such as the natural frequency analysis. So through the joint research and our own research, we want to really make an advancement of the algorithm development so that we can commercially use quantum computing for the different applications. So with that, I have explained the Q-Park, Kamui, Curie parts, and also our collaboration research. I hope if you have any intention to use or to learn the quantum computing, or I'm sure that there are different needs to really make the advancement. I'm waiting at our booth, so please stop by at our booth. That's all from my side. Thank you very much.